All right, so we just did U on the seesaw. All right. All right, now I have the exact same picture as I did last time. Okay, I have my wrench. There's my axis A. All right. Now the only thing I added, all right, so there's the applied force. Okay, is I added, besides showing the moment arm. Okay, so there's my line of action. Okay, that's my line of action. And then I drew a perpendicular line from the axis of rotation to the line of action. Okay, there's my moment arm right there. Whoops. All right. And then in this picture, I included a distance r. Okay, so essentially r is from the axis of rotation to where your finger is pushing. Okay, and then I also included this vector r. So vector r is just a vector from the axis of rotation out to where the force acts. Okay, because before we looked at torque in terms of force times moment arm. Okay, but we know that force is a vector. So I want to show how torque can be also related to two other vectors. Okay, force and that vector r. Okay, so again, so there's your hand. You're applying a force. Okay, and then I drew the vector r from the axis of rotation out to where the force is acting. So this arrow shows the direction of r. So r points in that direction. Okay, that's the direction of r. Okay, so the vector r, okay, terminates right there. Okay, so that I don't want. Okay. All right. So we said that torque is the applied force times the moment arm. So looking at the picture, okay, this moment arm, you have a triangle right here. There's your triangle. Okay, and so your angle phi for your triangle, okay, that angle phi for the triangle, okay, if I look at the sine of that, I'm over here. So the sine of the angle phi is opposite, there's your opposite, okay, over hypotenuse. And the length of the hypotenuse is the length r, the distance from the axis of rotation to where your force acts. So if I solve this, okay, if I solve this for the moment arm, that says that the moment arm is r sine phi. Okay, so we said that the torque, due to that force about axis A, is the applied force times the moment arm, but the moment arm is r sine phi. Okay, now all I did on the next step is, instead of F times R times sine, I just swapped F and R, and I wrote it R and F. Okay, now why am I doing that? Because you can either think of the torque as the force times the moment arm. Okay, now remember, the moment arm comes from drawing your line of action. You got to draw the line of action, then you got to go to the axis of rotation. Okay, and draw your dotted line, your dotted perpendicular line. Okay, or you can look at it in this case that the torque is the magnitude of r. So here's my vector r. So it's the magnitude of r, okay, which is just that length. Okay, so magnitude of r, okay, times the magnitude of the force times the sine of the angle between them. Okay, because here's my vector r. Okay, there's vector r. It points in that direction. Oops, it points in that direction. Right, that's the direction that r points. Okay, so this angle phi is the angle between the direction that f points and the direction that r points. Okay, so now we have two different ways to look at torque. It's either force times the moment arm, but again, to get the moment arm, you have to draw your line of action. You got to draw that perpendicular line, or it's just the distance r, which in this case is the length of the wrench, times the force. Okay, not drawing any line of action, times the sine of the angle between them. Okay, which is sometimes easier because then you don't have to draw the moment arm. All right. Okay, now, so r up in the picture is a vector, and the force is a vector. So you can actually define torque in terms of the magnitude of these two vectors. So we'll see soon that torque is actually a vector. Right now, we're not worried about the direction of the torque. We just want to know that it is actually defined in terms of two vectors. Okay, now, we've introduced a new quantity just recently, torque. Let's look at the units. Okay, well, again, think of torque as force times the moment arm. Okay, so what are the units of force? Force in newtons. Okay, forces in newtons. What's the units of R? Well, that's a distance, so that's in meters. So torque is in Newton meters. All right. Now, you might also see other units of torque as foot-pounds. Okay, so there's your force, and there's a distance. Okay, so it has units of force times a distance. Okay, so foot-pounds. All right. Now, it depends on what thing you're talking about. So even if you have a car made overseas, okay, which might use the metric system, okay, in terms of the bolts or whatever, when you look at the manufacturer's spec, they'll probably give you the torque, okay, that the car is able to, or the truck is able to produce in terms of foot-pounds, okay, probably because they're comparing it to the American-made cars, which is their competition, okay. So torque is always in force times the distance, okay, Newton meter or foot-pounds. But the weird thing is we know from the previous chapter that a Newton meter is a joule. So it's like, well, why not call torque joules? Or the units of torque joules? Well, it wouldn't be wrong to write torque in joules, but joule is usually reserved for an energy, okay, kinetic energy, potential energy. Okay, torque always refers to, or usually refers to, a force acting over some distance. Think of a hand on a wrench. So it's customary to give the units of torque as a force times a distance, either Newton meter or a foot-pound. Okay. Now, in this picture above, okay, that picture above, all right, we can see that any force that passes through the axis of rotation causes no torque. So in this picture, and I was going to get messy, okay, if there's your hand and you were going to push, okay, on the wrench, okay, that pushing arrow would pass right through the axis of rotation, and there'd be no moment arm. Okay, so any force that passes through the axis of rotation, I'll do example below here, causes no torque or exerts no torque about that axis. Meaning, when you go to screw in a light bulb or unscrew it, you don't push on the light bulb. Okay, you have your fingers, when you go to twist it like a jar lid or the lid of your water bottle, your fingers are a distance from the axis of rotation, they're out at the radius, and you twist it. Okay, so the torque always refers to a twisting. You don't push on the light bulb, you're twisting it. Okay, so we like to think in this chapter that torque is the rotational equivalent of force. All right, and again, eventually we'll see it's a vector. But in the early chapters, right, there's maybe your glider, you applied a force, and we said the object accelerated. Now you're going to apply a torque, there's the force, okay. That would be the vector r, that'd be the vector f, that'd be the angle between them, okay. So we're going to see that instead of applying a force and the object accelerates, now you're going to apply a torque and the object is going to rotate and have an angular acceleration. Okay, so that's eventually where we're going to go with this. Okay, now the important thing is you don't have to have a rotation to have a torque. Okay, going way back. Okay, the original picture. Okay, so remember, torque is a measure of the tendency, okay, of the force to cause rotation. Okay, the definition of torque, remember, torque was force times moment arm. Okay, as long as there's a force, as long as there's a moment arm, that force applied a torque. It doesn't say anything that something has to be rotating. Okay, so if here's your hand up here, okay, and you're pushing with a force of 10 pounds and it's not enough to loosen the bolt, okay, you're definitely applying a torque, okay, because you're applying a force at a distance, at a moment arm, there's a torque. You don't necessarily have to have rotation. So rotation is not in the definition of torque. Here's some more examples of a force applying a torque, okay, about that axis A. Okay, so I want to look at these one at a time. So let's look at this first one right here, number one. Oops, number one. Okay, so here's the hand, okay, and it's applying a force on the wrench. Okay, it's trying to twist it. Let's just say if this is a bolt resting on the table and the wrench is on the table. Okay, let's say for all practical purposes, you'd be trying to loosen the bolt. Okay, the bolt would come up, up out of the page. Okay, because you'd be loosening it. It's right-handed threads. Okay, so in this case, so here's the force. Okay, there's your force. I drew my line of action. Okay, for force number one. All right, and remember, torque is force times the moment arm. Okay, so you draw your line of action. Okay, it's an infinitely long line. Remember, the whole business is you could be standing over here 3 miles away with a rope pulling, okay, or you could be way over here with a long stick, right, a 1 mile long stick, pushing on it. Okay, the wrench just thinks it has a force of whatever that magnitude is at that orientation. Okay, so the finger doesn't necessarily have to be touching it, right? You could have a string far away or a pole pushing on it. Okay, so you have to have, that's the reason of your line of action. That's the motivation for a line of action. And then for the first one I drew here, here's my perpendicular line from the pivot point, right, the axis of rotation, to my line of action. That's my moment arm. Okay, now, if I keep the force the same, okay, I'm not going to change the force, all right? So if I reorient my force, I'll call this one number 2, all right? What's changed? Well, here's my line of action for force number 2. Okay, there's my line of action. And then to draw a perpendicular line from the axis of rotation, okay, all the way to the line of action, okay? There's my right angle. So that's my moment arm. Oops, this is my moment arm for number 1. This is my moment arm for force number 2, okay? So how did I change the torque? Well, I didn't change the force, okay? But what I did is I increased the moment arm, right? That's now bigger, okay? This picture here, okay, this picture here shows same wrench, okay? There's a bolt here. I didn't draw the bolt, but I got some bolt here, okay? And now my hand is here, okay, gripped around here, and I'm pulling on the wrench, okay, to the right. All right. Well, what's the torque about axis A due to the pulling force? All right. Well, here's my line of action. All right. And now what I'm going to do is I'm going to calculate the torque, force times moment arm, due to that pulling force. Okay. So it's the force. Let's say the force is 5 pounds. So it's 5 pounds times the moment arm. Well, how do you find the moment arm? I have my line of action, and now I'm going to draw the perpendicular distance from the pivot point right here, right there, okay, from the pivot point to the line of action. Okay, ready? There, I just did it. I'll do it again. I just did it. Okay, so the line of action passes through the pivot point. Okay, there is no line to draw. The distance is 0. Okay, so the moment arm, whoops, my moment arm is 0. All right, look at this picture down here. Now I'm pushing. Okay, I'm pushing on the wrench. Okay, so that pushing force passes right through the bolt. So here's my line of action. Okay, if I draw my moment arm, okay, the moment arm is the perpendicular distance from the axis of rotation right there, okay, to the line of action. Okay, there's no line to draw. The line of action already passes through the pivot point, so there's no moment arm. Okay, so that force causes no torque. Okay, so any force that passes through the axis of rotation causes no torque about that axis of rotation, right? So if you ever use a wrench, okay, now if it was a box wrench, it might make more sense that it was closed. Okay, don't worry about that. Okay, but you know that you don't pull on a wrench, and you know that you don't push on a wrench, right? The whole idea is you grab it and orient your hand so that this thing will have some tendency to rotate. Okay, okay, now, okay, so this picture, that torque is 0, okay, about axis A. This force exerts 0 torque about axis A. Now, how do I maximize the torque that force exerts? Okay, so again, torque, force times moment arm. Well, the idea is you want to maximize the moment arm. How do you maximize the moment arm? Well, you push on the wrench in that direction. Okay, so here's my same force I was looking at before. There's my line of action, right, my line of action. And I draw a perpendicular line from the pivot point to my line of action. There's my right angle. So that's my moment arm. So I maximize the torque by maximizing the moment arm. Okay, so here my moment arm is the entire length of the wrench. Okay, so that's why if this is your wrench, okay, and there's your bolt, okay, you don't take your hand and put it there and push. Okay, it doesn't make any sense, right? The idea is you want to maximize the torque by using the entire length of the wrench. Okay, so here's a short wrench. Okay, for maybe getting to tight spots, but here's a short wrench. Okay, so you apply a force. okay? Your torque is force times that moment arm, okay? And let's say the force is not big enough to loosen that bolt. You're trying to loosen the bolt, okay? Well, let's say this is the maximum force for you, okay? You can't apply any more force, okay? How do you increase the torque? And remember, torque is force times the moment arm. Well, you can't change the force, okay, but you can change the moment arm. So what you do is you get a pipe, oops, that's a pipe, and you put it around the wrench, and now you use the same force, and you put your hand there, and you push, okay? So what's changed? Well, the force is the same, but now the moment arm, which used to be this, okay, that used to be your moment arm, okay, is now maybe 1, 2, 3. Maybe the moment arm is now 3 times longer, right? Here's your axis rotation, and I draw a perpendicular line from that pivot point to my line of action. There's my line of action, okay? So what I've done is I've tripled the moment arm, okay? And so now, now that moment arm is 3 times bigger. So I've tripled the torque about that axis, okay? Now, the most important thing from this chapter is that a pipe is not always the best solution, because sometimes if you use something like this to multiply your torque, sometimes you rip off the head of the bolt, and now it's another 3 hours of work.